All right, so I've recreated the circuit that I proposed last night here for the LiBCM current sensor power disable. It's a high side P with an NFET control and then a low side in. And this almost certainly works, but I've had so much fun with this combined circuit already that I just went ahead and decided I had to test this to make sure that the voltage isn't rising too far here or dropping too far here. So let's look at how we have this set up here. First up, I've got 3 separate power rails here. I've got a 12 volt rail, a 5 volt rail, and then this is replicating the current load basically. So I'm just using this in current mode, and I've got this wire wound through here 8 times. So any current we force through here will be multiplied by 8. So 1 amp is 8 amps, 10 amps is 80 amps, 20 amps is 160 amps. You kind of get the drift there. And we can change whether or not it's regen or assist by just flipping the leads around, since this is only a single quadrant supply. So from there we have the actual output, which is ISOC. And I'm just feeding this through a resistor chain here to get close to the 82 ohms. I'm not quite there, but it doesn't really matter. And then I'm dropping that into our 5 volt rail, positive. And then I've got the negatives shorted together on these supplies, and I'm powering this with 12 volts. This is the 12 volt rail that we generate on LiBCM. It's always turned on. If the IMA switch is turned on, this is on. You can't turn it off. And this is the negative, which is the engine ground, which is used throughout the car. It's brown, yellow in the car. And so this is the enable circuit. It's a 5 volt enable, and you can see I've got this set up to current mode on channel 1, which is the 12 volt rail. And you can see that we're pulling 13 milliamps on the 12 volt rail. And you can also see that we're pulling about 1 milliamp on the B rail. And that will increase, of course, as we push current through here. So, for example, I'll go through, we'll come look at this. Here's how the current mode works. Right now I have it set to 10 amps. The voltage doesn't matter as long as we don't hit it. This is going to push 80 amps through. You can see that now the B rail is pushing 21 milliamps. That's the 5 volt rail is sinking 21 milliamps. And the A is still pulling about 12 milliamps. So that actually doesn't change a whole lot until you start sourcing a lot of current, which that's 80 amps. That's pretty high already. And so you can see that the voltage drops correctly as you would expect. If we flip the mode around from, I guess that's regen to assist, by flipping these leads around, now the current will go through the other way, and you can see the voltage rises as you would expect. This is just measuring the V-sense, which is how we do it in the device in the car as well. This lead coming out goes to V-sense. Now we do a divide by 2 and then we go through an offset and gain. That doesn't matter. This is a completely separate block. However, because again this is giving me so much fun, now that I've validated this first part, I'm going to go ahead and stick this circuit here, I'm going to stick it on the LiBCM PCB, which will give us the second stage, and that'll make sure that everything has remained linear and whatnot. I really don't want to spin this PCB again for one remaining issue here. This is the only technical hurdle that's still been bothering me. So all of this has been with this whole circuit enabled, and this circuit I pulled out some old patch board here, and man, I forgot how good this stuff smells. I'm sure that half the chemicals in this have been banned at this point, but you can't recreate the smell. It's really, really awesome. And so I've got all the things labeled here, sense plus, sense minus, 12 volts plus, and ground. And this is the sensor enable. So watch here now as I disconnect it. So now we're disabled. Current drops to 0. Current B drops to 0. Even if we push current, which is really odd, I wouldn't think that would exist, because that would mean the 12 volt rail was off and the key was off, but you were somehow pulling current. I mean, maybe that's a valid use case. I don't know. Anyway, we continue to pull no current, and it makes sense because 2 of the 3 leads here are floating. They're very high impedance. I couldn't actually even measure them with my just little off-the-shelf fluke here. I would need like a NI 4071, which has like a 10 giga-ohm range, to be able to measure the off resistance there. So it's essentially no current. It's certainly 5 to 10 orders of magnitude less current. Probably not 10, but it's certainly 5 orders of magnitude less current than the rest of the system we use. So no longer an issue. And then again, you can see that when we connect the enable, that the current goes up. We go back to 13 milliamps. So hey, look, this part of the circuit works. again, it's not a terribly complicated circuit. At least this stage, it's literally just 2 power switches that are turning this thing on and off. So yeah, I'll get this in the LiBCM, and we'll make sure that everything works. Again, the main concern I have is that as we start pushing 35 milliamps through these FETs, that the voltage starts to rise. It doesn't really matter because that's not going to affect our gain. The sensor raw current here this is a current source. So the current sensor here, which is off to the left, is an ideal current source. It's a current controlled current source. And it doesn't really care as long as we don't get once we convert the current to a voltage going through these resistors here. It doesn't matter if there's noise on these rails or if they're fluctuating. It only starts to matter if you get within the headroom, which is about 4 volts from positive to the raw and 3.5 volts from the negative to the raw. I wrote it earlier, whatever it is. But of course, I'm going to get the scope on there. This was just the proof of concept 1 to make sure that I correctly soldered this together. 2, that it intuitively makes sense. It is intuitively working as I would expect. And I wanted to show just one final thing here. This is 160 amps equivalent. And watch the voltage here. I mentioned this on the forum. So we rest at 5 volts here. And when we turn this on, we only go up to 9.2. Now this is higher. We're only expecting to go to 140 amps. I think 150 is kind of my limit. But this is 160 again. So you can see that we're about 9 volts. I was saying high 8 volts the other day. We've probably started to compress into the headroom of the supply. We could actually see if we start to dial the current back down. Yeah, you can see how we're at 9.25. So you can see that up to about probably 16 amps, so 16 times 8, whatever that is, we're fine. And then above that, we start to have problems. You can also see the current consumption through the rail. This all is looking peachy. Notice again that even as we go to higher currents, that's 25 times 8, that's 200 amps. You can see we don't actually pull any more current. We've kind of saturated the output of this stage here. Specifically, we've saturated the ISOC into the V positive. And then, of course, if we flip around the other direction, a little warm. It's a really thin cable to be pushing 20 amps through. So if we go the other way now, you'll see the exact same thing. Of course, this is regen, and we don't have as much regen capability. This is 64, 70 amps or whatever. You can see we've dropped down to 4 volts. This would be 8 amps here. And you can see again as we start to push down that we kind of run out of room at 3.75 volts. I think I said 3.5 volts. Sorry, my hand's in the wrong way. I think I said 3.5 volts is the headroom here, but it's actually about 3.75 volts. But again, this is much higher. This is 15 times 8, so that's quite a bit of current there. 34. That's 120 amps of regen. I think that we don't go past about 75. So anyway, circuit is working as you would expect. And then again, if we're in a high current state and we turn it off, we float back up to the 5 volt rail. Now the 5 volt rail is dipping here, but that's only because actually I don't know why that is. Actually, it's not dipping at all. You can see when I turn it off, it's just changed slightly. This is a crummy power supply. I pulled it out of a trash can at NI 15 years ago, probably more than that. And it was broken when I got it. I replaced the capacitors inside of it. It still kind of works, but it is a little bit noisy. But again, that noise shouldn't really matter. The 5 volt rail shouldn't even really matter either, so this should work just fine. Again, this is a proof of concept test here, and what I'll do now is I'll take just this PCB and I'll wire it up in series where it needs to go. I'll basically just cut the iSense raw and on the PCB, on the LiBCM PCB, and then put it in right there or wherever it goes. Yeah, we'll see you in the next picture. Thanks for watching, as always. In conclusion, this works.